Hello once again, class, and welcome to another mock lecture. Today, we're going to be talking about rational functions, which are composed of polynomials. So we're not quite done with polynomials yet. We're going to talk about the functions where those polynomials are divided. So we're going to start off with the definition. It says a rational function is a function f represented by p of x divided by q of x, where p and q are both polynomials. Of course, q of x can't be equal to 0, because then you'd be dividing by 0, and if you do that, the universe explodes. So it can't be that. But in general, the domain of these functions are all real numbers x, right? X element of the real numbers, such that, is what that vertical bar reads, x is not equal to k. And typically, that's where this stops. But the k that x can't be equal to is the thing that makes the denominator 0. Now, a couple things real quick before I look at a very quick example. Nobody writes this in pre-calculus. This entire class is mostly working on a domain of real numbers. You don't really start talking about complex domains until complex analysis, which is way later. And so typically what we would do is we would just write something like x such that x is not equal to, and then some numbers there. And those numbers are going to be whatever makes the denominator 0. So let's look at a quick example so I can hopefully make this make more sense. Suppose f of x is equal to 2x minus 1 divided by x plus 3, right? And what I want to do is I want to find the domain. I just need to figure out, well, what makes x plus 3 equal to 0? So I'll set x plus 3 equal to 0, and I'll solve for it. You just have to subtract 3 from both sides, and you get that x is equal to negative 3. So that's the thing that x can't be equal to. And that's it. That's all you have to do to find the domain of a rational function. In general, it's all real numbers, except whatever makes the denominator 0. Now you might be wondering, well then what's happening at x is equal to negative 3, right? Because the things that we were talking about before were polynomials, and polynomials had what we said, a continuous domain. There was no discontinuity in the domain at all, but this thing does have a discontinuity, right? Right in the middle of the graph, x can't be one of the numbers. So this is a good question. What is happening at x is equal to negative 3? Well, here's the graph of the function. And kind of as you can see, the graph is not very decisive in what it wants to do, right? I mean, here's negative 3, and as the graph approaches negative 3 from the left, it's like rocketing upwards towards positive infinity. But as you approach negative 3 from the right, well, then now it's approaching negative infinity. The graph is going down towards negative infinity. So it's in polynomial end behavior, where as x approaches infinity, f of x could either rise or fall, right? Approach infinity or approach negative infinity. This is like end behavior, but happening in the middle of the graph. It's like middle behavior of the graph. That's kind of what an asymptote is doing. It's forcing your f of x values to approach some kind of an infinity right in the middle of the graph. That vertical line that your graph is kind of approaching from either side is called a vertical asymptote. Now, a vertical asymptote is defined to be some line. Moving on. I'm just kidding. It's some line x is equal to k, where f of x approaches infinity or f of x approaches negative infinity as x approaches that specific value k from either the left or the right. So here I have it approaching it from the right. Here I have it approaching it from both directions. Here I have it approaching it from the right, kind of again. But the fact of the matter is, if there is some x value, whereas your x values approach that specific x value, and then your graph starts going down or up towards negative infinity or positive infinity respectively, then we know there exists this line called a vertical asymptote. And I think conceptually, you want to think about asymptotes as guidelines for your graph. Your graph kind of wants to go towards them, but they typically, especially in the case of vertical asymptotes, never reach the line itself. They never intersect the line. Now you notice that our graph also has a horizontal line that's acting much the same way. It's pulling the graph down towards it. Again, because a graph kind of gravitates towards its asymptotes, and there exists vertical asymptotes, but there also exists horizontal asymptotes. And a horizontal asymptote is some line y is equal to b, x is equal to is a vertical line, y is equal to is a horizontal line. But in this case, y is equal to b, where f of x approaches b as x approaches positive or negative infinity. So this is end behavior, but for rational functions. Turns out that rational functions will typically, well, I guess most of the time, not always, approach some specific value. right? Whatever b is. Here it's like some negative value. Here it's 0. Here it's like some positive value. But as x gets really, really, really big, as x goes this way, y gets closer and closer and closer and closer and closer to this value, whatever this specific value is. That's what a horizontal asymptote is doing. Now, there's two ways to find these things. One of them, you can just look at the graph. So like, for example, here's a graph. Typically, asymptotes are denoted with this kind of dotted line here. So we can actually see, right? The vertical asymptotes are x is equal to plus or minus 2. The horizontal asymptote is y is equal to 1. Right, here's another one. This one appears to have no vertical asymptotes, again, because there's no random discontinuity in the middle of the graph, but it does appear to have a horizontal one. Y is equal to 0, because the graph is being pulled towards the x-axis. But it seemingly is never going to reach it, just based on the behavior of the graph. The second way that you can find asymptotes is you could actually use the function itself to find them analytically. So what do I mean by that? Well, to find asymptotes, we're going to let f of x be p of x over q of x, and it's going to be written in lowest terms. To find the vertical asymptote, all you're going to do is you're going to set your denominator equal to 0, and you're going to solve that denominator equal to 0. If k is a 0, then x is equal to k is a vertical asymptote. Now you might be thinking, well, hold on, isn't that exactly the same thing that we did to find the excluded values of the domain, right? To find the things that aren't supposed to be in the domain? No, kinda. See, the difference is this, right? I mean, it is the same thing that we did when we found excluded values of the domain, but you do that before you simplify the function. To find a vertical asymptote, you have to simplify the function first. That's what lowest terms means. So like, for example, if we have this function, and I called it f again, that was kind of lazy. Could have called it something else. G? I think I used that later. L? Anyway, consider this function x plus 1 divided by x squared minus x minus 2. If I'm going to find the domain of this thing, I need to find what makes the denominator 0 right now. So before I simplify anything. So I noticed I could factor the denominator, and there's two things that make the denominator 0, right? If I set this equal to 0, you can just use the factor theorem at this point, right? 2 and negative 1 are the things that make the denominator 0 here. But it simplifies, right? The x plus 1 in the top cancels with the x plus 1 factor that's in the denominator. So this whole thing simplifies into 1 over x minus 2. Now there's only one thing that makes the denominator 0, and so that is where our vertical asymptote is. So I like to think about the excluded values of the domain as like, these are your candidates for being vertical asymptotes. Maybe both of them are vertical asymptotes. Maybe only one of them is. Maybe neither of them are, right? That's possible as well. In this example, there was only two candidates, but it's possible to have maybe like there's a quartic function in the bottom. So you're excluding 4 things from the domain. So there could be up to 4 vertical asymptotes. You have to simplify your rational function to see if that's actually the case. This thing is the actual vertical asymptote, because it's still the thing that makes the denominator 0 even after we simplified it. Which I think leads to another natural question. Okay, well, if at x is equal to 2, there's a vertical asymptote where there's the y values are approaching infinity or negative infinity. But then what's happening at negative 1? Because apparently we're not allowed to even plug that into this thing either, right? Because this function came from this one, and you can't plug in negative 1 to that thing. Well, here's the graph of our simplified function, 1 over x minus 2. And here's the graph of our function f. What's happening is that there's this like open dot in the middle of the graph at x is equal to negative 1. And you could actually figure out where that dot is because you could plug negative 1 into this. Right? You have 1 over negative 1 minus 2. So it's negative 1/3. So the open dot is at negative 1, negative 1/3. Right? That's what that point is right there. So yeah, sometimes there's just these open holes in the middle of your graph as well. And that also would count as a discontinuity. That one's actually called a removable discontinuity. But anyway, that's how you find vertical asymptotes. Set the simplified denominator equal to 0. To find horizontal asymptotes, it's actually kind of not very mathy. What you're doing is you're actually going to be comparing the degree of the numerator against the degree of the denominator, and one of 3 things is going to happen. Number 1, the degree of your numerator is going to be less than the degree of your denominator. And if that happens, y is equal to 0 is always the horizontal asymptote. The second thing is that the degree of the numerator could actually be bigger than the degree of the denominator, and if that happens, there just is no horizontal asymptote. And then the last thing that can happen is the degree of the top and the bottom could be the same, in which case you're going to get a non-zero horizontal asymptote. That's actually the only time you can get a non-zero horizontal asymptote is when the degrees are the same. To find it, you take the leading coefficient of your numerator, I called it a here, and you divide it by the leading coefficient of your denominator, so y is equal to a over b ends up being your horizontal asymptote. So let's look at some examples.
X sports. It's in the game.
Example number 1. Find the domain x and y intercepts and the asymptotes for this function, which I called g of x. So it's 2 over x squared minus 9. And we're just going to go in order. First, I'm going to find the domain. Now, anytime I'm finding the domain and I've got some nonlinear function in the denominator, I always factor it first. So I wrote it as 2 over x minus 3 and x plus 3. What makes the denominator 0 are the excluded values of my domain. So I can't plug in 3 or negative 3 to the function because that would make it 0 in the denominator. So here's my domain, x such that x is not equal to plus or minus 3. X and y intercepts, I'm having us find this here because the next thing we're going to do in a different video is we're going to learn how to graph these things. And finding x and y intercepts is a crucial part in doing that. To find an x-intercept, you have to think about what's the y value at an x-intercept, right? Well, I mean, here's some random function like this. Well, the y coordinate right here is 0. So to find the x value, just plug in 0 for g of x, and then you can solve for x. The thing about this, though, is it's a rational function. So the first thing that you'd always do is you'd multiply both sides by the denominator to cancel that out. So you really only have to set your numerator equal to 0. Let me just say that again real quick. To find the x-intercept, you set the numerator equal to 0. I didn't actually write that on a slide anywhere, and I don't really want to write it out in this pen, so I'll just say it a third time because it's that important. To find an x-intercept, you set the numerator equal to 0. Well, in this case, if you do that, you get a contradiction. 0 is not equal to 2, and whenever that happens, that means that there's just no x-intercept. To find a y-intercept, it's actually a little bit easier, but again, the same sort of question. What's the x-coordinate at a y-intercept? Well, it's also 0, right? Here's a function. There's a y-intercept right here. That x-coordinate is 0. So if I want to find the y-coordinate, just plug in 0 to the function. So I'm just finding g of 0 here, which gives us negative 3 times 3 in the denominator. So negative 2/9 is going to be the y-coordinate, which means our y-intercept is going to be 0, negative 2/9. Okay, as for asymptotes, nothing cancels, right? There's no x plus 3 or x minus 3 up in the numerator to cancel with one of these things. So in this case, the excluded values of the domain just straight up become the vertical asymptotes. Okay, so that one's easy. To find horizontal asymptotes, notice that the degree of the numerator is 0 and the degree of the denominator is 2. So if you go to this, we're in this case, right? Degree of numerator less than the degree of the denominator. So y is equal to 0 is going to be our horizontal asymptote. And just for completion, this is what the graph looks like. So you'll notice it's got the two vertical asymptotes at negative 3 and positive 3. It's got the horizontal asymptote at y is equal to 0, which you can't really see because the x-axis is on top of it. But you can gauge that based on the end behavior of the graph. And then also notice there's actually no x-intercepts. But there is a y-intercept right here at 0, negative 2/9. Example number 2. K of x is equal to x squared minus x minus 6 divided by x plus 2. Again, let's start with the domain, and the only thing that makes the denominator 0 here is negative 2. I don't even have to factor the denominator here. It's just, it's already factored. It's a linear factor there. To find x and y intercepts, though, I will simplify. So that's another thing I didn't really say at the beginning, but when you're finding x and y intercepts, you're allowed to use just the simplified fraction, which in this case is just a line. It's just x minus 3, which means that our x-intercept is when you set the equation equal to 0, you get 3, right? 3 is what makes it 0, so 3, 0 is the x-intercept. And then the y-intercept, I mean, it's a line. It's y is equal to mx plus b, So b is negative 3, so 0, negative 3 is going to be your y-intercept. And then it's a line, so it has no asymptotes, right? I mean, you can think about it as a fraction if you'd like, but there is no denominator, so you can't set it equal to 0 and solve. And also, the degree of the top is 1 and the degree of the bottom is 0, so according to this thing, it's also none, right? There's no horizontal asymptote when the degree of the numerator is greater than the degree of the denominator. This is what the graph looks like, and you'll notice that the only thing, I mean, it's the line x minus 3, but the only thing that's different about our graph is that it came from here, right? And this has a restricted domain. That's why there's this open hole here at negative 2, 5. All right, the last one we'll look at is v of x, which is equal to 2x squared minus 3 over x squared plus 1. The domain is interesting here, because if you try to set x plus 1 equal to 0, you get imaginary stuff. And it would be kind of funny to write, well, it's all real numbers such that it's not these two not real numbers. Right? That doesn't really make any sense. So instead, we just say it's all real numbers. You can plug whatever you want into this. The denominator can't ever be 0. Also notice that because it factors, I mean, I would say it doesn't factor, but we know that it does now. It factors into x minus I and x plus I. That's definitely not going to cancel with any of the factors for this, right? In fact, that numerator, I think, factors into 2. Oh my gosh, actually, what does it factor into? Well, let's see. If you set it equal to 0, you'd get x squared is equal to 3 halves, and then you square both sides, so you get x is equal to plus or minus the square root of 3 halves. So it factors into 2x minus square root 3 halves. Oh my gosh, my handwriting is terrible. And then x plus square root 3 halves. So yeah, it definitely doesn't cancel with anything in the denominator. So all of that to say, we'll just use this function as the thing to find the x and y intercepts. So first, to find x-intercepts, remember all I need to do is set the numerator equal to 0. Oh, look, we're doing exactly what I just did. Okay, there we go. I don't even need to explain that. Plus or minus square root 3 halves is when the numerator is equal to 0. So these are our x-intercepts. Square root 3 halves, 0, and negative square root 3 halves, 0. To find the y-intercept, all we do is we plug in 0 for x. So we get 2 times 0 squared minus 3 over 0 squared plus 1, which is just going to be negative 3 over 1, which is just negative 3. So we got 0, negative 3. And then we can talk about the asymptotes. Now we've already discussed how there's nothing that makes the denominator 0, and it doesn't simplify, so there's no candidacy for there being vertical asymptote x values. So there's just none of those. As for horizontal asymptotes, notice that the degree of the top and the degree of the bottom are both 2. So we're in this situation, which means we need to look at the leading coefficient of the numerator and the leading coefficient of the denominator and then divide those two by each other. So we would get 2 over 1, because we have 2 over 1 as the leading coefficients of top and bottom respectively. So y is equal to 2 is going to be the horizontal asymptote. Okay, so here's what the graph looks like. 0, negative 3 is the y-intercept. We've got our two x-intercepts at these values, although this one's here and this one's over there. There's no vertical asymptote at all. The domain appears to be all real numbers because there's nothing that's breaking the continuity of the graph itself. And then y is equal to 2 is the horizontal asymptote. I also just noticed that this says example 2, but I'm pretty sure this is the third one. Anyway, that's going to be it. Just wanted to do those 3 examples on how to find domain, how to find x and y intercepts, because that'll be useful for graphing, and also how to find the asymptotes, right? Really the guidelines of the graph. And the whole point of doing this is so that eventually, when you're graphing a rational function, and the first thing you do is you find your vertical asymptote, you find your horizontal asymptote. Maybe you discover that you have a y-intercept up here and an x-intercept down here. Well, then the only thing that could happen is the graph might have to do something like this, right? And that's kind of the direction that we're headed. So all of those things play an important role when you're finding the guidelines of the graph, which are called the asymptotes, and the intercepts, because graphs always want to tend towards their asymptotes. But anyway, hopefully you guys learned something. If you have any questions, please leave a comment below or shoot me an email. Thanks a ton for watching. and I'll see you in the next one.